All right, well, thank you so much for the opportunity to speak today about what the DOE and in particular NETL are doing to address the issue of orphan wells in the United States. So as most of you probably know, the bipartisan infrastructure legislation provided for funding to tackle this complex problem. And the relevant language in the appropriations is that we are to be conducting research and development activities in cooperation with the IIJA to assist federal and state and tribes in identifying and characterizing undocumented orphan wells and also mitigating the environmental risks of undocumented orphan wells. And this is a 5-year program. And the budget is $30 million, and it is, you can see, split between 5 different national labs that are participating, in addition to NETL, which is my employer. Sandia, Lawrence Livermore, Los Alamos, and Lawrence Berkeley National Labs are also participating. So the situation with orphan wells in the United States is such that because oil and gas development began way back in 1859 when the first oil well was drilled, you can imagine that the record keeping back then and in the early decades of oil and gas development were pretty insufficient for, according to today's standards, for being able to locate and characterize the wells. So that there are many wells for which the records that we have are somewhat inaccurate or just incomplete. They don't include a lot of information, or there just aren't any records at all for a specific well. So that makes mitigating this environmental issue very challenging if we are still having problems with locating and characterizing these wells. So the way the bipartisan infrastructure law program is designed, the Department of Energy is tasked with addressing undocumented orphan wells, figuring out how to locate them and characterize them using some of the tools listed there: remote sensing, data analytics, sensors and monitoring, geophysical characterization. And then on the other end, the DOI and the BLM are tasked with the actual mitigation, the assessment, plugging, and surface reclamation of wells once they've been transitioned from the undocumented into documented. And so when we look at this as a research and development program, what we're attempting to do is develop tools and techniques that state agencies and the DOI and BLM can use to locate the wells, evaluate things like ownership, well construction, what surface equipment is still in place, and environmental impacts like air emissions and impacts to water resources. If you look at the number of orphan wells across the country, the estimates vary widely because there's a lot of uncertainty there. But we do know that there are hundreds of thousands of orphan wells in the United States. And if you look at the graph, this shows by state the estimates of orphan well numbers. This is from the IIJA. And the states with the, kind of like the top 5 highest numbers: Pennsylvania, Oklahoma, Ohio, New York, Kentucky. These are some of the wells with the earliest development. And in the graph, you can see that documented wells are the kind of green color, and then the estimates for undocumented wells are in the yellowish color. So pretty big range in what kind of problem this is from one state to the next. But because the wells are undocumented and these are just estimates, there's definitely a lot of uncertainty there, and certainly room for research and development to try to be able to find all the wells and characterize them so that they can be eventually plugged. So the bipartisan infrastructure law has provided $4.7 million that will be available to the DOI, the BLM, and states and tribes for well plugging. And if you look at, for instance, New Mexico as an example, currently they've been plugging something like less than 50 wells per year. So this additional funding is really significantly going to ramp up all of those plugging activities in the states where these undocumented orphan wells are. As a national lab group, what we're attempting to do is develop a program that's comprehensive such that there's a wide range of usability here. The tools and techniques that we're developing can be used from anyone to a citizen scientist with a smartphone, moving to a more technically trained staff where we can do at the wellhead assessments, use things like remote sensing, like satellites or drone-based studies, and also use things like natural language processing, GIS analyses, et cetera. And then more to like a very specialist knowledge kind of resource where we'd be doing 3D modeling, integrated analyses, specialized measurements, et cetera. So this wide usability spectrum allows each state agency to develop their own mitigation strategies based on the resources that they have. One of the first things that we did as a group at the DOE was to do a survey of the states in the IIJA to try to figure out what current state priorities look like. So the survey was sent out through the IIJA, and we had 37 respondents representing 30 different states. And we got responses that about 70% indicated a moderate or low priority for finding and characterizing undocumented orphan wells, mostly because of constrained resources. So a couple of the key questions from this survey, one was that the states were asked, what approach or methods has your state been using or contemplated using to identify undocumented orphan wells? And the top 3 responses were historical records, landowner complaints, and field inspections. And then another question was, what are your state's biggest data needs or gaps relative to undocumented orphan wells? And those top 3 responses were location, well construction, and mechanical integrity. Interestingly, methane emissions in the purple bar there was not in the top 3 highest priority areas there, but it is legislative priority in this program. So really what we are hearing from the states is that their approach to date has been largely labor intensive and not very technical. Really just states trying to identify where is a well and what's kind of like its current state status based on a visual inspection. And we're also hearing some things about state-specific local constraints on doing inspections. For example, Idaho's no drone laws that would limit use of drone technology for finding and characterizing wells. So this survey was a good starting point for us to design the program so that we could be sure we're addressing specific state needs and trying to come up with a program that would have research and development results that would be directly applicable and relevant to the states that are involved. So we identified 5 key focus areas for the program, being methane detection and quantification, well identification or locating wells, sensor fusion and data integration with machine learning, well characterization, and integration and best practices. So in my slides, I'll walk through each of these focus areas and describe what the plan is for the 5-year program, and even more specifically what NETL is doing or has been doing in these areas to give you a little more detail and background. And because this is a government program, we really can't do anything without having a great acronym, right? So we came up with this name for the program called Catalog, Consortium Advancing Technology for Assessment of Lost Oil and Gas Wells. So in essence, we are cataloging the wells, right? We're trying to find them and document them in a specific way such that decisions for mitigation can be optimized. All right, so let's start with the first focus area, methane detection and quantification. So this is something that NATL has been doing for quite a few years now, starting back in 2014, 2015. At that time, there was nothing in the literature about methane emissions from orphan wells, but we were, kind of seeing evidence of some of the unplugged wells that we are encountering in the field of having emissions. So we set out to develop approaches for how to measure the emissions. And since it hadn't been done by anyone before, we tested out a few different approaches, including using flux chambers, high flow sampling, handheld laser-based approaches, et cetera. And I'll show some more slides that give a little more detail there. But overall, our objective was to quantify the emissions of orphan wells, determine the magnitude of emissions in context with other oil and gas emission sources, and report out to the state agencies that would then have to be responsible for addressing the issues. So over the years, we have a handful of publications on this topic. So I think NETL is in a good position to further the technology in this area. So the real need here is that states and other stakeholders really lack a standardized method for measuring methane emissions and also for finding super emitters. I've been asked a lot lately by representatives from state agencies that are going to be tasked with, characterizing wells. How do you go about measuring emissions from orphan wells? There isn't really a standardized approach. There's a bunch of different technologies that can be used to collect the measurements, but they all have their pros and cons. And so depending on the state's needs, one approach might be better than another. And that's a little bit problematic because without the information and the training, the states are, may feel like they're not well informed on how to go about doing this. So what we'll be doing in the program is providing quantitative measurements of undocumented orphan well methane emissions, looking at a range of measurements from direct source emission measurements taken right at the well to remote sensing techniques like using unmanned aerial vehicles or drones, combining these methane measurements with machine learning algorithms that will help pinpoint leaks or areas with a higher probability of leaking wells. And then another thing is if required or when required to do before and after plugging and abandonment emissions measurements, how can that data be collected to verify the emissions reductions, which is an important data point for the DOI. It gives a metric of the success of the program, how much methane emissions reductions have occurred as a result of the program. So the methane detection and quantification, it really applies to both undocumented and documented wells. The approach for collecting the measurements is pretty much the same. So, in this case, the research is maybe not specific to undocumented wells, but we're planning the results to be helpful to the state agencies. At NETL, we've tested a variety of methane emissions measurement approaches. And as I said earlier, they each have pros and cons. So, some of the more quantitative techniques that we've used include high flow samplers and flux chambers, both dynamic, what we call bag sampling, and static. And then more recently, we're using some continuous monitoring techniques. And then more kind of qualitative approaches where you're just trying to determine, is a well leaking or not? So that would use tools like optical gas imaging or infrared cameras, laser-based sensors, gas detectors, and also gas composition analysis. And these different approaches can be evaluated using several criteria, including cost, how long it takes to collect the measurement, what's the accuracy or limit of detection, how easy is it to do, is the equipment field portable to get to a number of wells, and is it effective for any or many different well types? Because something that we've seen in encountering orphan wells in the field is that each one looks a little bit different in terms of what infrastructure has been left behind and what condition it's in. So is an approach, can you use it at most types of wells, or is it only applicable for a certain type of well configuration? So in evaluate, if the states are trying to evaluate what type of measurement approach to use, and we can provide information about these evaluation criteria, that would be a good starting point to be helpful. So at NETL, we've used several different approaches to measure the emissions, and this map just gives you really broadly kind of where we're at now in terms of how much data we've collected over the past few years. So the green dots show areas where we're currently collecting emissions measurements from wells, and the red dots show some areas where we've been there, collected measurements. We feel like we've characterized that area. So Kind of moving from the north to south, we've looked at a private property near Olean, New York, where we looked at about 77 wells, some of them unplugged, some of them plugged. We've been to 2 state parks in Pennsylvania, Oil Creek State Park and Hillman State Park. They're both in western Pennsylvania. Oil Creek State Park is in the area where the world's first oil field was. So these are wells really early development there. About half plugged, half unplugged. And in Hillman State Park, all of the wells there were unplugged. We've been to the Daniel Boone National Forest in Kentucky. And in fact, we're planning another trip there in November. So far, we've collected data for about 54 wells there, most of them unplugged. We've been to the Oologah Lake area, which is near Tulsa in Oklahoma, and collected data for almost 180 wells there, most of them unplugged. And then a private property near Midland, Texas, where there's a very large number of wells on this property. We've been to about 100 of them, and all of them are plugged. So this kind of gives you an idea of where we've been and where we're going in terms of emissions measurements. One thing that's been reported in the literature and that what we've found is that there does seem to be regional variation in average emission rates. So that's why we're going out in different regions in the US and trying to collect data to see, how can we better quantify those regional differences, how significant they are from one basin to the next. So I had to throw this disclaimer in here because in the next few slides, you're going to be seeing some specific products. Obviously, DOE is a government agency. We're not endorsing the use of any particular product or company or service. But in some cases, there's very few instruments on the market that do specific things. So it's kind of hard to get away from, showing specific products. So in the case of high flow sampling, this is an approach that we've used starting early on. We've found it to be pretty useful for measuring emissions from orphan wells because the instruments on the market, the high flow samplers that you can buy, are generally very field portable. They are designed for the natural gas industry, for people to go out and find leaks. So you can see in the picture there, the ones in sort of like a backpack unit. And it operates by pulling a large volume of air into the sampler so that you're kind of sucking in the entire leak, and then it's measuring the concentration of methane in the air, and with the known flow rate, you're directly able to get an emission rate of methane from the well, which is nice because there's a lot of instruments out there that will measure methane concentration, but not necessarily methane emission rate. So the unit we have was manufactured by a company called Backrack. Unfortunately, they no longer manufacture this instrument, even though it was heavily in use. So nowadays, there's a few companies that are putting out new upgraded, next generation high flow samplers that you can purchase, or you can make one, kind of make and test it in the lab and use it like a home built version, because the technology behind high flow sampling is not really terribly complex. So in any case, high flow sampling, the cost for a unit is somewhere in the neighborhood of $40,000. Time that it takes is pretty quick. You can get a measurement in less than 30 minutes per well. However, I'll point out that this is like a snapshot measurement. It's not continuous. So you're getting an emission rate at that point in time when you take the measurement. And this is important because we still don't know a lot about the temporal variability of emissions from wells. How does it change over time? So if there is significant temporal variability and you're really relying on that snapshot measurement, it could be over or underestimating if there's temporal variability. The limit of detection varies per instrument, but we've got, the Backrack unit ranges from 0.05 to 8 cubic feet per minute. The next generation version that we have from, it's called the Semtech. That's a much lower limit of detection, which is great. And I would say these units are very field portable. They're generally battery operated. You calibrate them with lecture bottles. So in terms of comparison with some other approaches, I feel like this one's maybe a little easier to execute. In terms of using it for different well types, you can put different attachments on the sample inlet side, so it can encompass whatever leak point is of interest. So if it's a potentially larger well with, you know, the whole wellhead with different flanges and et cetera, you can put a bag over the whole thing and use the high flow sampler that way. Or if there's specific leak points, or maybe it's just a little bit of casing sticking up out of the ground, you can just put the sample inlet directly to the leak point. However, this approach is not effective for buried wells. We've encountered a lot of cases where orphan wells have been buried either by something like strip mining, or maybe it's in you know, a farmer's field and they've just cut it off at ground level and buried it. So in those cases, we can't get accurate measurements using high flow sampling. Flux chambers is another approach that can be used for measuring emissions from orphan wells. And you can kind of separate flux chamber use into two categories, dynamic or static. Dynamic meaning you have a constant flow of air through the chamber and you're measuring the concentration of methane in the air going into and then coming out of the chamber. You have a known flow rate of that air flowing through. So with those concentration measurements and the flow rate, you can calculate a flux or an emission rate. And I've shown here that the chamber itself can be either rigid or not. So in the case of a rigid chamber, you can see in the photograph there, the one that looks kind of like a dome that's sitting over top of a well. And in the picture on the right, you can see where we've used a flexible bag to cover a well and somewhat seal it. So in that case, you know, the configuration of the wellhead is too difficult to build a chamber around. You can just use a bag, and it seems kind of low tech, but was also effective. So cost of using a dynamic flux chamber, the chamber itself can be done really inexpensively, you know, the materials used to make the chamber. So really the cost depends more on what kind of instrument you're using to measure the methane concentrations. For instance, if you're using a fancy cavity ring down spectrometer, those can be about $40,000, but they do give you really good accuracy and precision. This takes a little longer than high flow sampling, maybe 1 to 2 hours per well, but again, it still would be considered a snapshot measurement. And as I just said, the accuracy or limit of detection would depend on the methane analyzer that you're using. In terms of ease of use or field portability, this is a little more difficult because it requires building of the chamber and testing of it to make sure you know, the air in there is well mixed, and the portability, you know, not quite as field portable because you have to maybe potentially build this chamber on site. If you're using a dynamic flux chamber, you need a source of the air that's going to be flowing through the chamber, so like a gas cylinder of hydrocarbon-free air, for instance. And then it's probably going to require some post-processing of data because you're collecting the methane concentration measurements on site, and you're collecting the flow rate measurement on site. Probably later you'll go back and you know, calculate the emission rate. The effectiveness for different well types, as you saw, a rigid chamber, you can't put that over top of all well types unless you're custom building a chamber at each well. But a bag will work for awkward shapes and if there's a wellhead with multiple potential leak points. And then moving on to static flux chambers, I don't have a great picture of this because this isn't really an approach that NETL has been using much. But in this case, you're looking at the change of methane concentration in the chamber over time and knowing the volume of the chamber to come up with the emission rate. So static means there's no airflow through the chamber. You put the chamber over the well, the emission or the concentration within the chamber increases over time as methane's being emitted from the well. Cost here is the same as for a dynamic chamber. It depends on the cost of the analyzer, or in some cases, if you collect a gas sample every now and then and send them back to the laboratory, however much that laboratory analysis would cost. This is a longer term measurement. You can do it over days. So it might give a better indication of, or at least cover emission rates over a long enough time that you're considering the temporal variability. Again, accuracy and limitation and limit of detection would depend on the methane analyzer. And this is another, not so field portable approach, because you probably are going to be building the chamber to fit the well. And I point out here in red, the biggest concern we have that's using static flux chambers is that there's a potential buildup of methane in the chamber. If you're putting a, closed container over a methane emission source, that methane concentration could increase to explosive levels. So in designing this approach, you need to consider that and figure out a way to ensure that doesn't happen. Something new that we've been trying is continuous monitoring. We're collaborating with a company called EarthView. They have a sensor platform called Bluebird with an inexpensive methane sensor and telemetry, so that remotely you can look at methane concentration at a oil and gas site. So we're working with them to try to adapt this sensor platform to use at orphan wells. So they've worked with us to develop like a static flux chamber approach where their sensor is in use. The chamber is allowed to be static for a period of time, and then every so often the chamber is flushed and the measurement period starts again. So what we're going to be able to do is to get methane emission rates over time. So this will allow us to evaluate the temporal variability of emission rates from orphan wells, which we think is important, so that it will help us determine if you're going to use a snapshot approach like a high flow sampler, is that adequate for getting a methane emission rate, or do we need to be repeating measurements over time or using a continuous approach like this because emission rates are varying significantly. Okay, so those were all quantitative approaches. So if we look at some qualitative approaches, one is optical gas imaging, or using an infrared camera. And fun fact here, the videographer in that photograph is none other than Emily McLean, who was a former NETL intern and is now with Rystad Energy, and she's on the agenda. She'll be speaking to us later this afternoon. So she did good work on our team years ago, early in this program. With infrared cameras, this is qualitative because it allows you to see the emissions from the well, but it doesn't give you an emission rate. So you can see with the photograph on the right there, that's an image in infrared of a wellhead with this one flange on the side. If you look at the little inset, and I'll press play, this is like high sensitivity mode of the camera. So it's a little harder to see and it's kind of flickering, but you can clearly see that flange and where there's what looks like smoke coming out. So that's helping us pinpoint where the leak is from this well. And then we can direct our quantitative approaches at that particular point. There are a lot of handheld methane sensors out on the market. These can be like laser-based, like the one shown in the photo, or like a LEL type monitor. These are helpful for determining whether or not a well is leaking, but they don't have the accuracy or sensitivity to provide an emission rate. And then also gas composition analysis. You can collect a gas sample in the field, take it back to the laboratory, look at the composition. And in this case, you're not getting an emission rate, but at least you can determine if there are constituents other than methane that might be of concern. Some results that we've gotten in the past, kind of generally, if you look at these graphs for unplugged wells with the well numbers on the x-axis and the emission rate on the y-axis, you can see they all kind of follow a similar fat-tailed distribution that's characterized by what we call super emitters. So orphan wells have a distribution like this that's not uncommon for oil and gas sources, where a small number of wells are emitting a large proportion of the methane. And interestingly, so this is for unplugged wells. If we look at emission rates that we've seen from the plugged wells at which we've collected measurements, in those same 4 areas, we're getting essentially zero emissions from almost all of the plugged wells, but there was one in Oklahoma that we measured that had a really high emission rate. In fact, it was higher than all of the plugged wells in that area. So in this case, that one super emitter plugged well kind of really skewed our average estimates of emission rates for plugged wells. So, the super emitter problem exists for plugged wells too. All right, so we'll move on to well identification. I spent a lot of time on the methane detection because that's something that we've been doing at NETL for a long time, and we have a lot of data and experience there. But we'll move on through the other research activities, the next being well identification, or figuring out how to locate wells. Something that we've developed at NETL is the use of aerial magnetic surveys. This is based on the idea that a metallic cased well is oriented vertically, so it's perpendicular to the Earth's magnetic field. And therefore, if you survey an area with a magnetometer and make a map of the magnetic signals, the well will show up as a magnetic anomaly, like you see in the kind of the color map on the right. The little hot spots are all potential locations of wells. And this was done, that area is in Salt Creek oil field in Wyoming. So this approach is really successful. We've started out using manned helicopters equipped with magnetometers, and in more recent years, we've moved to drone-based technology to be able to find wells. Another approach that we've used is LiDAR. LiDAR surveys are similar. You can do them with the aerial vehicle, either manned or unmanned. And in this case, this is some images for Oil Creek State Park in Pennsylvania. If you look at the historic photo in panel A, you can see a hillside that's just peppered with oil derricks. And then if you look at panel D, that's that same area, that same hillside, an aerial view with the LiDAR data. And you can see these characteristic kind of bench features in the landscape, with rectangular flat areas that are characteristic of a well construction at the time, where you see in the image on the right there, an engine house, kind of a long rectangular shape with the oil derrick on the one end. So when we process the LiDAR data and can find these areas that have this rectangular depression with the the well depression on one end, that helps us identify wells also. However, I should point out that this approach is really only successful in areas where the ground has not been significantly disturbed. Like if it's been farmed, plowed, etc., you're not going to be able to see these features anymore. Something else some of the other national labs are working on is kind of like a smartphone application, a well finder app that utilizes prior DOE investment or experience with geolocation. This is something that we could potentially add to the preliminary geophysical reconnaissance, and it could incorporate both the magnetometry and the LiDAR information. And this is an attractive option because it can engage the public, and you can use it for outreach and education, and engage citizen scientists to help find wells. The next research area is sensor fusion and data integration. So one of the things that we're working on here is combining signals from various instruments and then using machine learning to help identify and characterize wells. So for example, if you have a drone equipped with various sensors, like maybe optical, like a video camera, some sort of methane detection, magnetometers, maybe LiDAR, etc., put the suite of instruments on a drone, do a survey, and then you can use sensor fusion and data integration to kind of combine the information from those instruments, couple that with machine learning to come up with an overall regional assessment of an area. Where are the wells? Where are the areas of highest risk of there being wells? What's the impact to the surrounding area? Can you detect methane, etc.? Also, we're looking at machine learning techniques such as natural language processing so that we can more automatically comb through all those historical records to get information about well location. And also, we're working on constructing a national wells database. So, state agencies maintain well databases. There are some current efforts out there to develop a national well database, but as of yet, this isn't something that's publicly accessible. And we'd like to make all of the information that we collect, all of the well locations that we either come up with ourselves or help the states to locate, all of that can be publicly accessible in a national database. Moving on to well characterization. This includes the methane emissions measurements, but also other subsurface and near surface characterization that would help inform mitigation. So what information do states need to figure out how to plug the wells? So this would include environmental impact assessments, like is there brine leakage, for example. Different methods that we're considering here would include electrical resistivity, conductivity, electromagnetics, seismology, ground penetrating radar. What can we determine about the subsurface condition of the well using surface-based assessments? And then also looking through historical records again, coming up with formal approaches for assessing well properties using the documents that are available, things like records and landscape imagery. And lastly, kind of the biggest activity here is the integration and best practices. So this is where we take all of the research, all of the results that we've developed as a part of this program and share it with the state agencies. So part of this activity includes really intense collaboration and engagement of the state agencies, the IOGCC, the DOI, the tribes, et cetera, and industry. What we want to be able to do is to make sure that we're developing tools and technologies that are going to be directly applicable and going to be used by the state agencies. So we're going to be constantly checking ourselves to make sure what we're developing is effective. And if you look at the map there and the graph, well, first, if we look at the graph, that's showing number of documented orphan wells by state. And we've kind of tried to focus on, maybe like the top 10 or so states there in terms of each national lab having kind of like an area of interest where we're going to be focusing our research efforts. So the map of the US there shows a little bit of that breakdown where we're covering states like, the whole Appalachian Basin, Texas, Oklahoma, Colorado, et cetera, and California. So those encompass, I think, almost all of the top 10 states with the highest number of orphan wells, because you figure, what's needed state to state can be different. What do the orphan well problems look like from state to state? We've already seen methane emissions can vary from one basin to the next. So we want to make sure we're covering all the, areas so that the tools and techniques that we're developing are going to work kind of across the country. So if you look at NETL is mostly covering the Appalachian Basin. We have our offices are in Morgantown, West Virginia, Pittsburgh, also Albany, Oregon. But we're right in the Appalachian Basin, so it makes sense for us to focus our efforts there. So something that we're doing as a part of this is coming up with field test sites where we can test and demonstrate some of the technologies that we're developing. So one test site that we're looking at is in Hillman State Park, Pennsylvania. So I mentioned we had already collected methane emissions measurements from wells in this park. We've also done aerial magnetic surveys using both manned and drone surveys. This is public land, so we have, cooperation with the state park. And we feel like we've got a decent characterization of the wells in this park. So we think it's an optimal place for us to use as a field test and demonstration site. So before I run out of time, just a quick summary. With this multinational lab DOE effort, we're trying to progress tools and technologies that can be used by state agencies and industry to locate and characterize undocumented orphan wells so that they can be moved over into that documented column and addressed for mitigation. So we'll be leveraging the expertise that we have within the different national laboratories and collaborating with our key stakeholders, again, being state regulators, industry, tribes, et cetera. And for implementation, we'll be looking at kind of current state of the art, developing new tools and techniques and field testing them and demonstrating them so that we can then turn those technologies over to those that would be needing to use them. So that concludes my overview of this undocumented orphan wells program. It was kind of a brief run through, this being a 5-year program and involving multiple national labs. It's kind of challenging to, cover all of the topics that we'll be researching in a short presentation. But of course, please feel free to reach out to me for more information or for some specifics on any of the research areas being conducted by NETL or any of the other national labs. So thank you.
Thank you, Natalie. We really, really appreciate you joining us. I, as a former archivist, I delight at just the notion of you reviewing historical records and finding these wells in places that otherwise are lost. That's like the Sherlock Holmes of orphan wells. I know it's 9:57, but there's two quick points if you can hear me all right. Am I coming through?
Yes.
Great. One thing I chuckled at the slide where the states had mechanical integrity and other items at a higher priority. And I think you rightfully flagged the methane emissions being something that's politically motivated or, something that's inspired by political energy. Something I was wondering if in your conversations with the states, wouldn't it follow that your methane readings would help determine structural integrity? I mean, they're kind of related. If you see something that's spewing methane for a time, greater than what would have been forecast, would that not imply certain characteristics about the wellbore or the casing or something of that nature?
Yeah, that's potentially true. We've kind of seen in the field, it's really hard to identify trends that allow you to predict well characteristics. For instance, in the same small area, like, that Hillman State Park is a good example. We looked at wells, all of those were unplugged. Some of them leak, some of them don't. Some of them have a wellhead, some of them are just a little bit of casing sticking up out of the ground. So it's really hard to get a sizable sampling such that you can start to see these statistically significant trends that help you predict things about emissions or well integrity. So one of the key problems we face is just lack of data. It's kind of challenging to collect these measurements. My field team, we're going out a lot of times in the woods, trying to find a small rusty wellhead that just blends in with everything else. And, so it's a challenge. And, we're every year have collected more and more data, but in terms of statistical strength, I feel like we're still not there yet.
That's the part of doing foundational work. And just one last question here for you on the temporal variability, and kind of gets to what you're already talking about it being very early on in the stage of you building this data set. But what have you been finding with those changes? Again, I know that's not necessarily statistically significant, and you're not speaking for all wells, and there's a lot of variance. But that being said, do you find from well to well that there is a number of ones that will have no emission event and then a big spike, or it seems rare to have one that's kind of constantly leaking day in, day out?
Yeah, so early on, one thing we did was we'd go back and do repeat measurements with a high flow sampler at the same well, just to see how repeatable our measurements were. And we found that on average, they were not showing significant variability from one sample to the next. However, that doesn't necessarily mean that that's not happening in reality. And you mentioned like no emissions and then an emission event. You can imagine, say, if you have a well that's filled with fluid, with water, and there's kind of like bubbling, almost like a burp of methane, then you might see it as no emissions and then a spike. So we haven't been able to actually capture that in any of our field measurements yet, but you can even just think about how that could happen. Another thing is that kind of anecdotally, we were talking with a company that was working on developing a continuous methane monitor and testing it at an orphan well, either on their property or close to their facility. And there was a Marcellus shale well being drilled and completed, I think less than a mile away. And what they were seeing in their data were changes in emission rate that seemed to correlate with activity going on at that shale gas well. So that's, again, something kind of anecdotal. We don't have any data to really prove or disprove anything like that, but that you can think how that could be happening too. So hopefully, you know, with developing these continuous monitoring approaches, we can evaluate situations like that, shed a little more light on exactly what we can expect in terms of temporal variability.
Certainly. And I mean, reserve engineers model how many abandoned wells are in, you know, around drill sites for that exact reason. It impacts the pressure of their bores. So Natalie, again, thank you so much. Incredible presentation. I thought you did a great job of giving such a good comprehensive view, and we appreciate it.
Okay, yeah, thanks for having me.